So I guess by popular demand, here I go again. Previous name of the session was the Neutron Beryllium. Now, well, experiences in using that Neutron ODL. So first of all, brief introduction. My name is Wojciech. I work for Cisco. I actually work for an engineering group, for the ODL engineering group. At Cisco, we have a solution, an NFV-focused solution that actually uses ODL and OpenStack to orchestrate, along with orchestration tools, to orchestrate basically a set of NFVs, etc. So the observations, as I call them, findings presented or summarized really in this presentation are the outcome of our work on this system. And at a high level, this system looks as follows. Basically, we're trying to make it fully HA capable. And at the moment, in its current release, it was only OpenStack that was ready for HA. The ODL controller was missing a couple of aspects like OpenFlow HA and netconf HA, which we're using. So it was just a single instance node. But the key thing is really the OpenStack cluster, which had several Neutron servers. And on the compute side, we used both OVS and non-OVS switches, also virtual switches to do the data plane forwarding. This testing was done, and this actually solution runs on Icehouse. It's in the process of moving to Juno. The findings apply in equal measure to these two. So the first observation when we've begun work on this is that actually the Neutron OpenStack ODL ML2 driver is evidently very much a single-threaded driver, and it simply blocks until ODL responds. So in this system of ours, well, we had a single ODL, and the throughput was really gated by the ODL response time. It's not a big deal for networks and subnets, but for port creation rates, it certainly was one. Now, the Neutron side of this equation, mainly the Neutron server capacity, of course, can be addressed by adding more Neutron servers, which we did in that cluster setup. And this, however, actually brought about a lot of the concurrency and race conditions, which I'll be focusing on the next slides. The way the OpenStack and ODL setup works is that there is basically a Neutron database that needs to be synced into the current Neutron northbound database. Well, there is inside the ML2 ODL driver, there is a rather simple sync mechanism that is meant, whose job it is to do the synchronization. And this sync mechanism, well, unfortunately, the way it's done leads to some classic issues, like this race condition, and actually called concurrency here, whereby we have Neutron node 1 that is asked to do a full sync, or it's triggered to do a full sync by some error. And it clearly will do the sync at time t1 using the Neutron database state present in Neutron database at time t1. So it starts off doing that, and then a second request arrives at time t2 to the second Neutron node to delete network A. This is a very small request. It gets passed down straight into ODL, and ODL, well, is very happy to remove that network A from its database at time t3. Now, unfortunately, node 1 only gets to process the update, the sync part of concerning network A at time t4. And it says, hey, it's not in ODL, we're out of sync, so I better go and push it back into ODL. So the end result is that really you've got even though you're trying to sync, you'll get out of sync, because the end state is that Neutron doesn't have network A, correct? But ODL has network A again, incorrect. And for the network, it's maybe not so much of a big deal. But for ports, basically, with this situation keeps on happening repeatedly, you get an accumulating amount of stale entries on the controller. It can also happen in some specific cases for creates and updates that basically it leads to, let's say, less evident but ever troubling issues around this time. For example, if T2 represents an update to a network A or to a port, and T1 is the full sync, then T1 will basically overwrite the update, so you got bad states on ODL. Okay, next observation is, again, concerning the sync mechanism. And the particular design of this sync mechanism has it run only kind of after being triggered by an event. These events today are basically any error events coming from ODL. So if ODL tells you it cannot create because the network is there, okay, we set this flag to sync, and on the next run of the Neutron server, we try to sync. So two key observations around this mechanism. One, today it's very indiscriminate in terms of under which conditions it actually runs or decides to sync. Basically, any error will do. And two, it only tries to sync at the next time it runs. So the next time there's a Neutron activity. And in a multi-node setup, this is an evident problem because, as shown here, at time T1, we've got, let's say, create subnet Y on network A, arriving into the Neutron server. The initial conditions are that ODL does not have network A, so it is out of sync. So clearly at T2, that subnet creation fails. Okay, good. Neutron server number 2 realizes, okay, I've got a failure, I'm out of sync. I'll set the flag, and I'll run the sync mechanism next time something is requested out of me. Well, unfortunately, the load balancing mechanism makes the next call go to Neutron server number 3. In this particular case, I'm showing that this is actually the same call because the user, let's say, is retrying or the client is retrying. And again, it will fail. So from a user side perspective, if you're using the Neutron CLI client, basically the symptom of this is that you gotta try it a couple of times and it works after the third time. You know you've hit this in a 3-node cluster. You know you've hit this issue. Or, well, any odd number of times when these nodes decide to flag as being out of sync. So it's very, at least there are repeat failures and occasional successes, and it's not a very pleasant system to work with. From a slightly different category, so moving away from the OpenStack ML2 driver into the domain of actual device configuration and making things gel. For those of you who've had experience with neutron networks, you know that ultimately a neutron network maps into a provider network. And provider networks need to be attached or told on which physical ports on the device they actually belong to. So it's those red lines down there, and I've got, let's say, a management network, provider network, and it's intended to operate on Ethernet 1 or port 1. OpenStack doesn't store this information today. It is something that OpenStack, sits outside the OpenStack, but is clearly important for the OpenStack system to run properly. And the way it is solved in the ODL plus OVS combination is that the operator needs to run a magic script, which you have to write yourself because it doesn't exist, On the compute node, that script, what it has to do is it has to set a particular OVSDB ID parameter that some OVS, the writers of the OVS driver code chose in OpenDaylight. And that parameter conveys the name of the network and the physical port it's meant to be on. And then it makes its way into OVS, and then when OVS connects using OVSDB to the OpenDaylight, OpenDaylight kind of acquires that information. So it's a very contrived process of getting at that information, which is actually, it's got nothing to do with OVS, nothing to do with OVSDB. It's basic network topological information. How a network maps to an interface. We found this problem to be acute because we also had other switches. And basically other switches, well, they don't use the same script, they don't use OVSDB, but everybody needs to know how to map a neutron network to their port. The solution to this that we have devised is basically, well, use ODL as the repository of that information, and basically in a device-independent way, so that you pretty much have just a neutron network, device name, and the physical interface it should map to. And this works across OVS or any other devices that you may have. Because we've chosen to do this using a Yang model, it automatically creates a RESTconf API, so it becomes basically a programmable API on the ODL controller. And the next observation is actually a pretty problematic one from the overall design perspective of the question.
Understand the previous observation. Are we talking about some heterogeneous topology that includes OVSDB, OpenFlow topology, and Beryllium devices?
Yes, well, so in this particular case, yes, we've had actually other virtual switches as well. And it's the same, I mean, every device that has a need to map a neutron network to some interface on which it wants that network to talk to that network, it needs this information. So to us, it just felt, it's the wrong place to actually, have this information being, stored or configured on the compute nodes using some dinky scripts, as opposed to it being in OpenDaylight, where actually it lends itself to being visualized operationally in terms of the topology, because this is topological information. You can visualize, physical network. I mean, port 1 actually has neutron network management. Right, and observation 5, as I was saying, it's a big one concerning the overall design of the existing way of communicating between OpenDaylight and OpenStack, and that is really that there is no feedback. So the only feedback mechanism that is currently provided by this by the way the two components communicate together is, if OpenDaylight accepts data, everything's good. If it doesn't, well, then it's really bad. Then you got sync and issues. But it doesn't cater to the case where, okay, OpenDaylight, the Neutron database accepted the data, but then there was a failure in actually rendering it into a network configuration. No, there is, so it's basically, well, there is a create network, and it goes into ODL, and ODL responds, yep, okay, I've accepted it in my database. I haven't done anything at all with it. There's no network configuration at all done, but That's as far as the communication goes. Now it's more, just 1 second. There is a little bit more to this because actually the way that Neutron generally works, it is generally port driven. So all actions on the network happen when there is some ports activity. So it's the port events that are kind of the worst ones. But yeah, sorry, question.
Is it correct behavior though? I'm not sure. For example, if we're not using OpenDaylight as the controller, we're using the vanilla one from OpenStack. Is it also the same behavior?
So so basically to paraphrase the question, is this behavior there also when not using OpenDaylight? And the answer is yes. No, so the answer is yes then, because the way this mechanism works with OpenDaylight or without is really, especially to the OVS case. So thank you for bringing it up. Is as follows: Neutron is told network. Okay, network is there. Neutron is told subnet. Yes, subnet is there. Great. The port information is the interesting one. Neutron is told to create a port, to get a port, and this needs to happen before Nova goes and does the VM. So Neutron goes and configures the ports, gets the port. Neutron database is fine. It says port is okay, and then tells Nova, okay, go and do the VM. Nova does the VM thing through Nova agent, and if the Nova agent fails at any time, in itself in configuring libvirt or in plugging OVS or in whatever, Neutron is still fine. Neutron says, well, if you look at the Neutron database, port is there, everything looks good, it was all accepted, but it was Nova that failed. If I may use an analogy, the architecture with this OVS piece particularly is one of, you have a PC, and it's the PC plugging itself into the switch. I think a better mode would be that the switch plugs the VM or the PC directly in terms of the Neutron component, doing the full end-to-end networking piece, as opposed to leaving this other thing to say, well, Nova, plug yourself in whenever you're ready.
So basically, Neutron is never sending the feedback of failures from Nova.
Yes. Now within the OVS agent, maybe this is my let's say lack of knowledge in that area. Maybe the OVS agent, which we're not using in the ODL case, has some mechanism to provide that feedback, kind of to back that out. But in the ODL case, it's certainly not there. So this leads to a problem that's, well, if you're looking at the Neutron state, Neutron logs, everything looks clean. You got to find, the issue on the Nova logs, or maybe you got to find the issue in the OVS DB logs on the host machine.
Usually you find that problem in the OVS agent log or the DCP agent log.
Yes. Now, in this case, we do not. In the ODL case, we would not have the OVS agent log, so because there's no OVS agent, so it's certainly an issue. Now, in general. Yeah, the behavior was, as I mentioned, I think the desirable behavior would be more like the one I mentioned earlier, which is that if there's a network failure of any kind, it should be fed back in through Neutron back into the Neutron database. So I didn't mention the solutions, but we have kind of partial solutions to some of these problems. These are not easy problems to solve. They require, my goal here is to make people aware of the problems so that we actually can start working on a community solution. I think there are changes in OpenDaylight and ML2 needed. In the kind of interest, I guess, engineering interest here, we have some fixes or enhancements to these mechanisms that make these problems much smaller. With this one, for example, we patched the ML2 driver, and to minimize the number of full syncs that it does. Basically, do not do full sync stupidly randomly, or semi-randomly, but maybe just do a partial sync or do a single resource sync. So you have the smaller window of opportunity of getting trapped into this. With this particular one, we had we changed the logic and not to do the sync next time we run, but retry a sync while immediately after the error occurred. So there are fixes here and there. Overall, this mechanism and the current communication mode is a bit creaky, so it requires further thought. And we'll be certainly documenting these problems for future reference.
So just one comment. If you look at the open stack rule, right, when something fails, you get feedback. It shows maintain premise, and it comes back and says there was an open network. Maybe it's possible that there could be some kind of calling that you can have for Nova in OpenDaylight, so that can get some kind of feedback from you, because definitely there's some way of getting feedback, and it's something to make good use of.
I mean, here it depends where the failure occurs, but the obvious piece is the kind of the hardest one. The last piece of the cable not connecting, because from the Horizon dashboard everything looks running. Neutron looks green. The VMs are running because they're running, but they're just not connected. So.
The domain of the SDN. Because if we look at this as a physical switch, and the physical computer is unable to belong to that switch, the SDN controller doesn't have to belong.
Anyway, I'll be around, so if you guys have any more questions, let me know. Thanks.